Okay, we are now coming to the last invited talk in this in today's track, and our next speaker is from a company. I'm willing to bet everybody in this room uses this company. I've been using it all day, trying to tweet and point to blogs I've put on LinkedIn. So Deepak is at LinkedIn. He's their main big data analyst, leads the machine learning optimization team. He's had a distinguished career in research, including Yahoo. He's a fellow of the American Association for the Advancement of Science. AAAS? American Statistical, fellow of the AAAS, American Statistical Association. And he is going to tell us how machine learning is being used at LinkedIn for optimization, I hope. All right. Thank you.
Thank you all for coming. I would like to begin by thanking both Rajesh and Osama for the kind invitation. In fact, I would also like to congratulate for putting together such a great session. The quality of the talks so far have been outstanding, and I think it will be outstanding tomorrow as well. So again, I think we should all give them a round of applause, if you don't mind. So again, as Osama said, so I have the privilege of leading a team at LinkedIn, an awesome team at LinkedIn that is using data mining and machine learning for improving LinkedIn's product. And in the next 30 minutes I would try to provide you a glimpse of all the work they have done in the area of recommendation, search, and advertising at LinkedIn. So so first let me tell you something about LinkedIn. So how many of you are on LinkedIn? Show hands. Okay, great. So almost everybody. And for those of you who are not, it's never too late. So I'm hoping you're going to join. And again, I don't have business cards, so if you want to connect with me, you have to connect with me on LinkedIn. So you better get an account, right? So what is LinkedIn? So let's begin with our mission. So our mission is to connect the world's professional, to make them more productive and successful. Now, you cannot make professionals productive and successful only by helping them find a new job, right? You also have to make them better at what they're doing today, right? And again, I think we have just gotten started. We have around north of 370 million members. But according to our estimate, there are like 3.3 billion members in the global workforce, right? So our aspiration or our vision is to be able to create economic opportunity for every single member of the global workforce. Right? That's really what our aspiration is. So how would we do that, right? So we'll do that by creating the first economic graph of the world, right? Now, what is this economic graph? So this is a graph. Again, we are all data scientists. We understand graphs very well. So the nodes of these graphs consists of the following entities. First, every single professional should be on this graph. Every single company on the planet should be a node in this graph. Every single job openings they have should be on this graph. All skills required to get these jobs is part of this graph. Every single institution you need to go to acquire these skills. All the knowledge you need, professional knowledge you need to become better at what you do every day. So these are all the nodes of these graphs. And once we have created this graph, we want to facilitate the flow of capital, all forms of capital through this graph, right? That's how we are envisioning in terms of creating this graph. And again, this is not just a vision anymore. I think we are kind of finding this to slowly come true, but still we have a long way to go, as I was mentioning. So the next fundamental question, again, this is a great vision statement and a mission statement. What does it mean to me as a data scientist, right? How are we going to facilitate the flow of capital through this graph? So again, let's see. So the first thing is to make the graph accessible, right? If you can't even make the graph accessible, if you can't search the graph for every single entity, you're not going to have capital flowing through the graph, right? If I'm a recruiter, I want to be able to search for the right candidates. If I met someone at this conference and was inspired by their talk, I want to look them up on LinkedIn by searching them on LinkedIn. If I just heard about a new startup at this at a conference, I want to look up that company on the company page on LinkedIn. If I heard about a news, professional news, I want to go and search for an article on LinkedIn. So that's the first functionality. You need to be able to search all entities on this economic graph. Then we need to be able to connect members with other members on the economic graph so that you can avail of future opportunities that may come your way, right? And again, connecting with people is not enough. You also need to nurture these connections, as we all know, right? You connect with a person, you take a business card, and then you throw it in the dustbin. That doesn't work, right? You need to nurture these connections. You need to keep in touch with what is going on in each other's life. So that's again another component of kind of making having capital flow through this graph. If we want to make sure that you are able to read articles from trusted sources, that would help you become better at what you do, right? We want to make sure that if you're looking for a job, we are able to connect you to the right job on the platform. We want to make sure that if you are a student and you're looking for your next move, we are recommending you the right university you can go to so that you can fulfill your career aspirations. If you're a professional, we want to make sure that you can acquire the skills that are going to help you go to the next step, right? So this is how we kind of facilitate the flow of capital through this graph. Now, if you think about it for a moment, every single thing, every single example I gave you is a matchmaking problem, right? You have a user, you have a contextual information. The contextual information could be a query or some other device or other things. You have an item set, and you want to figure out how to match them, right? So this is the problem we as a community know how to solve, right? I mean, I was looking at the proceedings, and almost 40% of the papers in the proceedings this year is about this matchmaking problem, right? And so we know how to do this. And again, if there is one message you want to take out of this talk is, data mining and machine learning is going to play a fundamental role in creating the first economic graph of the world, right? Again, with that, let me kind of go a bit into the details of how we are going to do this algorithmic matchmaking, as we call it. So again, I think it's not very surprising to this audience that a very practical way of doing that is by learning continuously from the data, right? By building machine learning and statistical models that can help you do this matchmaking, by running experiments. And again, we have heard a lot about running A/B experiments at the conference. Ronnie gave a great talk yesterday on the subject, so I'm not going to belabor that point. But one thing I want to mention is there are two different kinds of experiments when you're doing these matchmaking problems. One is the A/B test experiment, where you're testing two different procedures. The other is doing adaptive experiments to make a given procedure better by collecting the data you need to do a good job of doing machine learning and statistical estimation. And again, just as the first A/B test kind of has parallels to what FDA does to test drugs, this is also known as adaptive clinical trials in the literature. And so, for instance, if you're running a trial for treating patients with cancer, new cancer medicine, then for ethical reasons, you don't want to do a randomized experiment. You want to do an adaptive experiment so that you can save as many patients as you can during the trial itself, right? So this is similar to that, and also called explore exploit in the machine learning literature. I'm going to talk about it a little bit later. Now, this is all great, but we cannot continuously learn through the data if we don't have a scalable and robust infrastructure. That's of paramount importance, right? So you need a robust infrastructure to do large-scale batch computations. And again, Hadoop has emerged, of course, as an undisputed leader. And we heard all about Hadoop from Cloudera yesterday. We need to be able to do large-scale nearline computation. And again, for that, we use Apache Kafka. This is something that was kind of born at LinkedIn, and then we ended up open sourcing it. We need to be able to do high throughput, low latency online computations to meet strict SLA requirements when you're serving things to users. And of course, we need fast retrieval engines to be able to do effective search. Right? So this is the high level thing. So now let me begin with search, right? So I want to point out the main difference between search and recommendation. It's probably obvious to everyone here, but just to make sure we are on the same page. When you're doing search, the user specifies an explicit query, right? So when a user has told you that I'm looking for Osama Fayyad, well, then, you better have Osama Fayyad in your result set. If you show the users people who are similar to Osama Fayyad, the user is not going to be happy. They really want to know what Osama Fayyad is up to, right? Not really someone similar to Osama Fayyad. So, recall is very important in search. And again, that is not the case in recommendations. This is a fundamental difference between search and recommendations. Okay? And again, search at LinkedIn comes in different flavors. It is not like web search. It is kind of more narrow. But again, we go deep into that vertical. So first, of course, people search, as you can imagine, is the most important search at LinkedIn. We have recruiters searching for people. We have members searching for luminaries like Barack Obama or Amar Abdullah or George John or Waqar Hassan. So and we have users. You might have met someone at this conference, and you may want to look them up, right? So there are many different contexts in which we users kind of end up doing people search. You may have salespeople looking for decision makers so that they can sell their latest product to them, right? Then if you're a job seeker, we want to look for jobs. You might search for jobs. You might search for a company, and so on and so forth. Right? So search is a very critical component of what we do, right? And then let's come to recommendations now. So before getting into recommendations, I want to kind of again point out that there are two different mechanisms by which we deliver recommendations to you. One is, of course, the usual pull model, right? You come to the website, you go to the app, flagship app, and we kind of recommend you things on the app or on the desktop, right? The other is what, again, the pull model is generally used by users who are very frequent visitors to LinkedIn. The other is the push model, right? We have users who sign up, they get a job, then they disappear, right? They're not taking advantage of LinkedIn as they should. And so we kind of try to wake them up. We call them dormant users. So we wake them up by sending them high-quality emails. So again, how many of you think LinkedIn is sending you too many emails? Okay, so again, we understand that's a problem. We are working on it. Less is more. That's the new mantra. Again, I think, but again, more seriously, we are kind of building a system, again, based on data mining optimization, where the goal is to send you the right message to the right user at the right time, at the right frequency, and through the right channel. So you're going to see a lot of improvement happening in this area. I think we already have seen a lot of improvements, but again, we are kind of on it. So hopefully at the next conference, if I meet some of you, let's revisit the issue again, right? Okay, and again, this is all done through machine learning and optimization. I don't have time to go through this whole area, but this is very nice, very nice, beautiful set of optimization machine learning problem. You can do response prediction, and then you can write large linear programs and solve it under different constraints. Very beautiful theory. A mix of theory and data mining, right? So you can talk to me offline if you're interested. Okay, so with that introduction, in the rest of the talk, I'm going to kind of talk about some of the data and the problem formulation. I'm going to talk about the machine learning process we follow to scale machine learning for different applications. And finally, I'm going to end with some lessons we've learned in the process, right? So first of all, whenever we are dealing with a matchmaking problem, you need to know your users, you need to know your items, and you need to know the user's intent, right? So what information do we have about a user? So again, I think profile data is, of course, one of our important information. So for instance, if you look at this profile, you know the title of the user, seniority, skills, education, endorsements, whom they're connected to, what company do they follow, what articles do they read. So everything is here. Right? It's fascinating data, right? It never ends. So, okay, great. So, but again, things are not as rosy as I showed you, right? I mean, not every user has so much information. We wish everybody kind of gives us that much information, but there's a lot of heterogeneity in the area, and that's one of the challenges, right? How, given all the heterogeneity you have in the profile information, how do you kind of do inference at scale? Behavioral attributes, of course. We look at all the activities that the user has done on the network, what searches they're doing, and all that stuff to kind of figure out what they're interested in. And again, we are a social media company, so of course we look at your egocentric network and see whom you're connected to, whom are you sending emails. We don't read your emails, but whom are you sending emails, and whose content do you actually have a more affinity to, whom do you trust in terms of Hadoop, versus something else. So all that information is kind of used to construct machine learning features, which are again used across the board for all different applications. Okay. User intent, very important. Like, why are you here? Are you here to hire someone? Are you here to get hired? Are you here to stay informed about what's going on in your area? Are you here to grow your network? Are you here to nurture your network? Are you here to sell, market, and all that stuff, right? So that's very important. Sometimes it's very explicit, right? If the user is visiting the jobs homepage, you kind of know that they're searching for a job. Sometimes it's not very explicit. The users might be passive. They are very happy with their job, but they don't know there is an awesome opportunity waiting out there for them. So in that case, we might have to nudge them and kind of make them realize that there is something better that they can do to kind of move to the next stage of your career, right? So both explicit and implicit is very important, right? Things to recommend, as we already talked about that. We extract a lot of features out of our items. We have a separate NLP group that's kind of doing a lot of work in NLP to kind of do the usual thing that happens in NLP. We extract semantic features like topics, unsupervised. We run LDA models, as many companies do. We do a lot of work on profile standardization, right? So, every profile has different titles and different seniority. How do you standardize that into a standard taxonomy so that it can be used across the board, right? So that's, again, another thing we do, right? So, okay, with that, so let's talk about how do we formulate objectives to optimize. And again, I was very pleasantly surprised. This has actually come up a lot in the conference so far, so that's great. This is a very important thing which we all need to be cognizant of when we are solving this problem. How do we optimize these objectives by machine learning models, and how do we kind of automate this process to some extent? It cannot be completely automated, right? So again, so the first important thing is to kind of formulate your objectives in a proper way, right? So whenever you're kind of improving a product, there are some long-term objectives you want to improve, like return visits, total revenue, and so on and so forth. Once you know that, how do you formulate proxies that you can optimize readily by using machine learning and optimization, and they are going to move those business metrics, right? So that's actually a very challenging problem, as you've heard. Like, sometimes you may have to take linear combination of multiple things and do some longitudinal studies, see if there is correlation. Sometimes you have to do surveys. You have to remove the bias in the survey data and then figure out what combination works. In some cases, you may not even be able to figure out what these linear combinations are, and then you end up doing something like multi-objective optimization. Okay, let me look at the trade-off curve. Let me look at the efficient frontier and see what can I compromise to get what, and then I'm going to make a call in a big meeting with different stakeholders. So that happens a lot as well. And once you have formulated your objectives and proxies, then you kind of put it into machine learning module, and it kind of optimizes. You roll it out. You learn from it, you refine your objective, you keep iterating until you kind of get a good product, right? So we engage with the product, we experiment, we learn, we deploy, we innovate. And this is a continuous cycle. You cannot get it right in one shot, right? You have to continuously innovate, okay? So this is, again, a cartoon of how this works. Everybody here knows it. So, you look at your item bank, you do filtering, like you remove all the spam stuff, porn, and all that stuff, bad stuff. Sometimes, you also have to remove things that are unprofessional. We are a professional network. So, if you look at our feed, sometimes people share puzzles and other things. They are very engaging. In fact, I've seen many people click on it. I should not name who they are, but they're not professional. This is not consistent with the brand image of LinkedIn, so we end up removing it, right? So you have to detect what is professional, what is unprofessional. And again, that's a combination of man and machine, right? You cannot do perfectly with machine. So you have to get some label data from man, editorial, and then kind of feed it into a machine learning algorithm and learn it and kind of filter it out, right? So a lot of that goes on. Of course, we collect all the user data, and then you collect all the context data, put it into a machine learning algorithm, and then the machine learning algorithm outputs a bunch of scores. What's the probability of clicking this item? What's the probability of sharing this item? What's the probability of liking this article? What's the similarity of this article? What's the similarity of this profile with that profile, right? So these are kind of scores which you get, and then you take these scores and put it into a ranking module, right? So the ranking module could be either very simple, you just sort by CTR in some cases, or it could be complex, right? So it could be complex in the sense, you might have to take a linear combination of these scores. You might have to formulate multi-objective optimization. Sometimes there are business constraints. And, business constraint is not a very bad thing, especially since it's very hard to figure out what is the right thing to optimize for long-term business health. Sometimes intuition is good, right? I mean, if something doesn't look great, it's good to kind of keep that in mind and kind of learn from that, right? So I think business objective is bad if you have a very good understanding of the problem, but if you're still learning about the problem, it is okay to kind of not expose users to some bad user experience, right? So anyway, so that's the ranking model. So ranking model is more complex than the scoring module, okay? Okay. Okay, so I think to kind of make things more concrete, I'm going to focus on one recommender problem, which is the newsfeed. I think all of you, if you have signed into LinkedIn, must have seen the newsfeed once in your life, so you know what's there. So newsfeed is again a very important thing for LinkedIn. It's the starting point, right? This is where you start your journey on LinkedIn. You come to newsfeed, so you get a lot of user visits on LinkedIn, and then newsfeed kind of sends you to other pages on the site. Like if you are looking for a job, you send you to the jobs app, or you send you to the jobs page, and so on and so forth. So it's extremely important to get this right. And I think this clicker is not working. Okay. Yeah, so the number one thing is the newsfeed has a lot of different kinds of updates, right? So, there are updates where you can congratulate your friends on a job change and job anniversary. Then, if you are following Bill Gates and Bill Gates writes an article, you'll kind of get it on your feed. We also show you recommendations like articles and people recommendation, endorsement, and of course we also show you some sponsored ads, right, just to make sure that we can actually run the business, make some money. Yeah. By the way, so showing mobile, selling mobile ads on, selling ads on mobile devices is something we also do, right? So not the exception here. Okay. So the other thing is about the feed. Feed is again dependent, right? So if you see the same thing, if you see multiple updates from the same user in your connection, you kind of get bored and it starts decaying, right? If you see the same kind of thing on your feed multiple times, like you see only articles or only job, you have a tendency of kind of not engaging with them. So I'm going to show you some data around that. It's also not very clear what metrics to optimize, right? So you may want to optimize clicks, likes, shares, job applications, revenue. How do you kind of do a trade-off, right? So that's again very nice. So, however, the fundamental problem, as we know, is to kind of come up with a module to do response prediction, right? So what is the probability that the user is going to respond to an item in a given context, right? So this is a fundamental problem. Once you solve this problem, it provides a nice statistical framework for you to kind of add other downstream utilities and constraints and then kind of do the ranking, right? So I'm going to go a little fast here. I think I'm having some problem with the clicker. Okay. Yeah, so this is the click prediction. Again, you want to estimate the probability of a click. I'm just demonstrating with click, but you can use anything else, like, share, whatever, right? And, we use the good old logistic regression, scalable when understood. The challenges, of course, are the usual challenges. How do you integrate features from multiple sources? How do you scale the training on large data sets? How do you ensure that you can experiment very rapidly, and how do you do fast real-time scoring at runtime, right? So these are the main challenges. So the main features, sources for us is very obvious: user, item, context. Interactions are very important, right? So if you have an ad from a particular industry, then you want to know whether the person is actually from that particular industry or not. So those kind of features help a lot because it captures the affinity of an item to a given user, right? And again, just features is not good enough, right? It is hard to beat something like the total number of clicks by total number of views. If you have an ad or an item that has already received a lot of clicks, that's a lot of data, right? And we should be able to use that to kind of make much better prediction than constructing thousands of features, right? Similarly, there are many users who come to the site very often, right? So we have a lot of data about them. So like we have 400 million users, and if we have only 100 parameters for them, that's like 4 billion parameters. Now again, I can't use the term deep learning here because it's already taken, but maybe I can use something like smart learning, right? So we do smart learning with 4 billion parameters, right? So again, when you're talking about logistic regression, logistic regression is very powerful, right? It really depends on how you use it, what kind of features you're adding to it, right? So this is roughly the model. I'm not going to go through the math, but you can see, right? You have the cold start model. So these are all based on features, interactions, and these are ad-specific feature, right? So for every single ad, you have a parameter. For every single user, you have a parameter, and then you kind of try to estimate them as well as you could from the data. Okay, right? And again, model fitting. So model fitting, we use Spark, We have recently switched to Spark. We used to use Hadoop earlier. We use what is well-known ADMM algorithm. So, I think roughly speaking, this is how the ADMM algorithm works. So you partition your data into different chunks. You run a local logistic regression. You look at the estimates in each of these local logistic regression and see the deviation of every local estimate from the consensus. If there is no consensus, you iterate again, and you keep doing it until you reach consensus. Right? So that's the basic idea. Right? So in this equation, so in this equation, there is you run a local regression per partition. You look at the consensus estimate. If the consensus is not there, so the parameter U tells you how far you are from consensus. If you have not reached consensus, you again do another iteration. Keep doing it until you converge. And you can theoretically prove this is going to converge to the global optimum. Okay, so we use ADMM for all these things. We also have a system where it is very flexible for someone to add new features into the system, right? So this is actually very important for developer productivity, for data science productivity, right? Feature engineering is something that is extremely important. It generally improves productivity way more than kind of launching many different kinds of models, right? So we have a config-based system to launch model, right? So whenever you add a new feature, you don't have to do code push. You don't have to do service reboot. So you can just change your config file and it's going to automatically launch the model, right? So that helps a lot. And so this is how it works. Whenever you have to incorporate data from a particular source, you take the data source, you write a function, small function that's going to take the data source and convert it into a feature vector. If you want to do some transformation on the feature vector, like for instance, you might have taken the user data and you have created all the feature vector. Now, for a particular model, you want to just use a subset of these features. So you can call the subset transformer, right? So you can do transformation, and then the assembler pretty much takes all the features from the sources and transformers and puts it all together, right, for scoring. Oh, 10 minutes. Okay. And we make sure that the offline is in sync with online. So what do I mean by that? So if you do a transformation offline in your machine learning process, and you find that the new model you have developed is good, you can just easily launch it online, and the online will be able to just use the same transformation which you did offline, right? So config-based, offline and online in sync, this is how we kind of make this process very simple for data scientists to launch new model and keep iterating with new features, right? If you have a new idea, you want to use a feature that has been developed by team B, you're in team A, you can easily call the data source, create a new data source, put it into the assembler, it will all work, right? Okay. So runtime, again, very important for latency, right? So, there are several tricks we use here. First of all, like everyone else, we make extensive use of caching, right? Cache. Whenever, don't be lazy in your computation. Don't pre-compute everything. Only compute when necessary, and cache, right? That's really the main thing we do. Like for instance, in logistic regression, we have several partial dot products. You can easily cache them very easily, right? You can also cache feature vector, right? And if you find a new user and the feature vector is not in the cache, you can always impute some reasonable value from past data, and you spin up an asynchronous process that can compute these feature vectors for that particular reason and put it into the cache. So the next time when the user comes, you kind of have it fresh in the cache, right? So this is what is going on, and I'm just showing you an example here in production where we didn't have the cache versus when we had the cache. As soon as we remove the cache, you can see the latency spiking up, right? So caching really helps a lot in these applications. Okay, so this was all about response prediction. Now let's look at some other components. So the first one is, of course, explore exploit, which many of you are familiar with. So how do you predict the click rate of a new item, right? It's also called the cold start problem. You don't have any data for this item, so how do you do this? So the solution here is to run a controlled experimental design, right? So what do? You explore. You collect data by running a very small experiment where you promote this item out of order, right? And you use that data, you incorporate that into your model, and then once your model says this item is really a good one, then you start exploiting that item. So that's why it's called explore exploit, right? And again, I'm going to probably skip this slide. And so there are a lot of solutions to do explore exploit. The one which we use is again called Thompson sampling, and the idea is very simple, right? So So here, imagine a logistic regression in 2 dimensions. So these are your cold start parameter. We assume that there is no statistical variance in the cold start parameter because you can estimate the cold start parameter using tons of data in the past, right? The warm start parameter or the ad specific and user specific parameter is where you have all the uncertainty, right? So we estimate the variance of these parameters and then we just sample the coefficients from the posterior distribution of this parameter. So that's how Townsend sampling works. And it has been very effective for us so far in terms of doing explore, exploit. Impression discounting is again another thing. If you show the same thing to a user multiple times, doesn't work very well. You can start seeing the CTRs decay. So you have to do impression discounting. Diversification is again another important thing as I was talking about. For instance, here is an example. If you show 2 adjacent group discussions, the second one has a CTR which drops by 21%. 3 drops by 48%. And again, similar curve for actors. If you show 3 things from the same actor, the CTR kind of drops almost by half. Right? So you cannot show the same thing multiple times on the same page. You have to diversify your results. Right? And again, multi-objective I already talked about. So for instance, here is a formulation. I want to maximize the advertising revenue, but I don't want to lose more than 5% of the organic engagement. Right? And again, you can write down a linear program and kind of solve it. And you can get this what we call the efficient frontier, right? So how much revenue, how much engagement am I going to lose for different improvements in the revenue, right? So once you have the efficient frontier, then it's easy for the stakeholders to take a look at this efficient frontier and make a call. Okay, well, if I can only lose 1% revenue, 1% engagement and get 40% bump in revenue, that's a slam dunk, right? That's very easy. But if you get trade-offs that are more intricate, then you need more discussion, right? Okay, so how do we put it all together, right? So I've talked about various components, right? Impression discounting, response prediction, and multi-objective. How do you put it all together? So what we do is we do a federated model, right? So on tier 1, we build local models for different update types, right? So the jobs team will build its jobs model, the ads team will build its ads model, the people recommendation team will build its own model. We call these different local models and kind of blend them in tier 2, right? We calibrate across different update types. We do more holistic personalization by adding additional features on top of whatever they are returning us. And once we have done that, we re-rank that by doing diversification, impression discounting, and multi-objective optimization. If you want to know more about this, there is a separate paper from LinkedIn just talking about this stuff, so you can go to that paper tomorrow, I think. Scalable model building. So this is, again, very important. So the thing I want to point out here is we follow a separate process for doing quick research and development versus maintaining the model. Right? So we provide the researchers with a sandbox kind of environment where they can quickly test out new ideas offline. And once we have rolled out a model in production, you don't want the researchers to be babysitting those models, right? We want the process to be more automated and kind of run automatically over time, right? So this is something that we have built at LinkedIn. We always build a stack of models from simple to complex, right? If you don't build the simple, you don't know how complex your complex model is, right? So you need to go from simple to complex. And we have a feature management system so that different teams can share features across and incorporate that into your models, right? So going beyond machine learning statistics, dog fooding, again, this is something we do a lot, right? Whenever we launch out new product or new model, we are all going to look at our own experience, and if something looks off, we kind of go and debug the system. And there have been many cases where, based on our experience, we have found errors in our models or in our systems and so on and so forth. We often conduct focus research group studies. We do user surveys to kind of understand the sentiment and emotion of users. I mean, this is something which you cannot get from click feedback. You have to ask the users. Right? We often follow intuition and remove certain content types. Like, I don't want this content type to be on the feed because feed is not supposed to do this, right? Just as part of the product strategy, right? So we also do some of that. The presentation layer is very important. How much real estate you provide to different updates kind of makes a big difference in terms of the metrics. So that's also something which we optimize quite a bit, right? So again, just to summarize. So the number one thing, again, I want to re-emphasize, this has been already mentioned several times, problem formulation is very important. Again, this is something So, no matter how much work we do in automating machine learning, this part is never going to get automated, at least not in the foreseeable future. Right? This is where we need smart data scientists to kind of work with the domain experts and come up with the right formulation of the problem. It's better to get an approximate solution to the right problem than to get the exact solution to the wrong problem, right? So I think this is something very important to keep in mind. Machine learning is slow and fragile, right? So I think this is reality right now. It's not very easy to do machine learning, right? There are so many different components. You have to kind of pay very meticulous attention to every single component. One of them breaks, the whole system breaks down. So it's very fragile. All right. Model training, again, there have been a lot of emphasis in the literature on scaling up model training, but model training is not the only thing that matters. Right? Data pre-processing, feature management, nearline computations, online computations, these all matter, right? So I think model training is very important, but so are the other components. Unless we kind of build a holistic end-to-end solution, we are not going to be able to solve this problem, right? So we better pay attention to every single component, not just the model training component. We need infrastructure. Without infrastructure, this is not at all possible, right? This thing will become even more fragile, and it's not going to even scale, right? So we need infrastructure like A/B testing platform, fast retrieval system, nearline systems, key value store. These are all very important, right? And finally, when we are building these end-to-end systems, I think the data mining and machine learning people should be involved in the decision-making process, because often if you're not involved in these processes, you don't get what you need at the end of the day. Right? You should not delegate these things to systems engineers, although they're great, they're brilliant, but they don't understand the requirements of data mining and machine learning. Right? So it's very important to be involved in the process when this whole end-to-end system is being built. So with that, I think I'm ready to take questions. Thank you.
Yeah, I see a hand in the back. So.
Thanks for the excellent talk. My name is Yan Chen. I'm an active LinkedIn user. I use LinkedIn every day. Well, I'm also have a professional group on LinkedIn which has 14,000 members. I have a question regarding regarding your LinkedIn group owners, not regarding normal users. Well, my question is for group owners or group managers. Does LinkedIn provide anything for? I know LinkedIn provides group stats, but what I mean, does LinkedIn has any plan to provide for them more support or service to make it easier for group owners for them to develop the group? For example, generate every week these are the top hot topics, and all these other people top people who contribute to these topics, and who these are a couple of people who has those kind of expertise. A second question is, well, I wonder whether LinkedIn has a plan.
Can we make the question shorter? Do you get the first question?
Yeah, so I think that's an excellent question. However, and I know that we have an excellent product.
Can you summarize the question?
So I think the question was, can group moderators kind of get some additional visibility and benefits on the LinkedIn platform, right? Was that the question? Yeah. So I think we have a great product team working on revamping and enhancing the group's product completely. And I know they have a great product roadmap, but I don't think I'm going to be able to share it yet. But only good things will happen, so watch out.
Let's trust you on that. Question 2?
The second question is still regarding the group. I just wonder whether LinkedIn has planned to make group owners benefit from the group because they spend a lot of time and effort to manage that. For example, to help them to make a profit out of that. Yeah, thanks.
Yeah, so I think it's the same answer as question 1, right? So I think we have a good roadmap, and again, I'm not the product person running that product, so I don't want to comment on anything. But many of the things you raised, the product group is well aware of these things, and they are incorporating that into their future plans.
The joys of being at a public company. So, yeah, another question here?
Yeah, I have a technical question about optimization. For the logistic regression, you are using ADMM. Have you tried SGD or other coordinate design, these kind of methods?
Yeah, so we have we have tried all methods. Now we are on Spark, so it's very easy to try SGD, gradient descent. We don't see a difference in performance. Historically, before we were on Spark, we were using ADMM, and since the other methods didn't provide any improvement in our core metrics, we decided to just stick with that. But we do have other methods available to train if necessary.
Okay. There's a question right next to you. Yeah.
And you're using logistic regression, so that's actually a linear classifier, right? So
not quite. I think it depends. Yeah. It depends on the features, right? If you have nonlinear features, it becomes a nonlinear classifier.
So I wanted to ask. So you spend a lot of time doing feature engineering, and then you feed it into a linear classifier. I mean, you've got millions of features. How exactly do you do it? Why not explore something else, like some other nonlinear classifiers, other than logistic regression?
So again, this is I'm going to answer this question at a very high level, right? I think whenever you have a problem, there is some structure in your problem which you can exploit, right, to kind of solve the problem. In this case, it was the structure we had in this problem. I didn't go through that in detail. Is you have the cold start model and you have the warm start model. Now, once you train the coefficients on the cold start, you can easily partition the data by items and run a separate logistic regression for each item in parallel. This is embarrassingly parallel. There is no connection between the parameters at all, right? So you can scale this up in any infrastructure you have without any problem, right? So this is an example where you actually use the structure of your problem to scale the computation instead of using a more generic hammer, if you will, right, to kind of nail every problem, right?
Sorry, can I ask one more question?
Yeah, let me ask a question, and then who has a question? Sorry, I can't see. Oh, you do too?
Yeah. So
okay.
Still using simple quasi-Newton or Newton methods to train logistic regression? Or
sorry?
We can't hear you. Can you speak up?
Yeah, you're using simple quasi-Newton or to train logistic regression, or are you using out-of-core methods like?
So when we are using ADMM for every local logistic regression, we are using liblinear, which is basically using a trust region Newton method. It's a second-order method, so it converges very fast.
So I saw another question here. If you can, oh, it's back there, back there. So while the microphone makes its way, I'll ask my question. So Deepak, I need to make you a bit uncomfortable here.
I'm ready for it.
Yes. Share with us something that didn't work. Like you tried to crack some problem and it was either a horrible user experience or a really bad idea, or machine learning didn't work.
Oh, that is the bulk of what we do. Like most of the things we try don't work.
Pick one.
So again, I can share one on the feed. Okay, I am just thinking if I should share it or not. But yeah, so one thing is, so again, we all know matrix factorization is great and it has shown a lot of improvement in different products. So what we did was we tried matrix factorization to estimate a user's affinity to content shared by different users, and that didn't work. What really worked was a simple counting model, right? You just count the number of times you see a content from a user and number of times you click, estimate this affinity by using just simple counting model. That beat the crap out of matrix factorization. So this is very surprising. Right?
Thank you.
Now, I'm not claiming I did a great job with matrix factorization, but this is what we observed.
Okay, all the disclaimers. Yeah, did the microphone make it?
Yeah.
Yes.
So it's kind of a follow-up question. So though as data mining researchers, we focus a lot on complex models and accuracy, so how important is interpretability in an industry environment, at least in the LinkedIn environment?
Yeah, so this is a great question, right? So I think interpretability comes in handy when things go wrong, right? So if things go wrong and something is not working, how do you figure out what is not going wrong? There could be several reasons why things go wrong. Maybe the tracking data got broken, maybe the pre-processing step did not work, or maybe some feature transformation did not work. So in such scenarios, having an interpretable model comes in really handy. You can triage the issues very quickly, you can fix it, and then you can kind of be up and running. Right? If you have a very complex model, that does become an issue. The other thing is, if you have a simpler model, getting uncertainty estimates and doing explore exploit, that's another big advantage, right? So if you have a very complex model, let's say if you do neural nets, I think getting uncertainty estimates for neural nets is still not very well understood. So how would you do things like explore exploit? I mean, then you have to use some heuristic like softmax and other things, but then those things require a lot of tuning. So there is no free lunch, right? If you do something better, you have to kind of suffer in some other area. So I think interpretability is very important for us. We take it very seriously. But again, the answers may vary depending on the problem you're solving.
So before we bring this session to conclusion and thank our last invited speaker, I wanted to highlight that tomorrow afternoon you get a second chance to ask Deepak any tough questions that you haven't thought about. Same applies to a selection of our other speakers. So tomorrow we will have George John. I'm putting Rajesh on the stand as a panelist. Enough of the chairing. Amr Awadallah, Basil OJ, and Chris White. That'll be tomorrow, which will be the last slot in our fourth session of invited speakers. So with that, I'll draw the session to conclusion. Please join me in thanking Deepak.